Hi, my name is Mark Davies. I'll be presenting a masterclass on the Mantra renderer and advances in Houdini 15. So I've prepared a bit of a presentation. There'll be portions of it that will be done through slides, and then we'll walk through some examples with the renderer itself. So I'll first give you a bit of an outline in terms of what we'll be covering in the presentation. The first topic we'll look at is rendering engines in Mantra. There's a wealth of different types of rendering that you can do within Mantra, different architectures that are present. And we'll talk a little bit about advantages of each of them and best use cases for them. We'll then look at PBR and path tracing, which is basically the physically based rendering architecture that's present in Mantra. We'll look at variance, often a source of artifacts in our images, especially dealing with PBR, is variance, or as you might know it as noise. And we'll look at different sources of noise and how to combat them. We'll look at quality metrics. So this is one of the advances that we've added in Mantra 15, dealing with different ways of measuring quality of the render and tuning it to get the best out of the renderer. We'll then look at adaptive sampling, some techniques for reducing noise in the renders again. We've got a section on texture baking, which is quite exciting as an addition to Mantra, being able to bake out UV maps and using different formats like Ptex and UDIMs. We'll then look at surface baking, which is concerned with baking down surface and geometric detail into texture maps and things like normal mapping, occlusion, dealing with displacements as well. And then we'll look at a time saver, which is render checkpointing, the ability to restart renders that have been interrupted. So on the subject of rendering engines, there are multiple rendering architectures supported in Mantra. They are titled engines in terms of their globals and their parameter name. There is the micropolygon engine, there is the ray tracing engine, and there's the PBR engine. And so the question that often comes up is, what is the difference between these various engines and which one should I be using for my project? And so we'll look at each of them in turn. Micropolygon engine is related to the Rays algorithm, if you're familiar with it, very much based on the work that you can see with RenderMed and other A-buffer methods. The whole idea is that the geometry is diced according to screen projection at a fairly high degree of accuracy. Displacement shaders and such are run against that, but the actual finite primitive that you're dealing with is a micropolygon, which is, you can think of it as a pixel projection of your geometry. So it's quite small in terms of screen space, and it allows high detail in terms of shading and displacement. Another characteristic of the micropolygon engine is low memory footprint. Because it is dealing in an A-buffer format, only data in the active tiles in the image space are being processed together. And so that means that you don't have a high degree of memory use. You have each tile, occupying as much as it needs to in terms of memory overhead, and they are discarded on completion. And so the other characteristic that we have with the micropolygon rendering is often the shading is decoupled from the pixel sampling. So you can choose a shading rate for your geometry that is different from that of the actual pixel geometry that's being sampled in terms of the image buffer. And so this is done through interpolation. The micropolygons are diced and their vertices are shaded. And then in the actual pixel sampling, we're blending across those micropolygons to achieve the actual shaded values. And so you can have quite coarse shading metrics compared to a fine pixel sampling ratio. So that gives you a little bit more flexibility. In Mantra also, micropolygon rendering can be mixed with ray tracing. So the techniques for actual intersection can be different from your traditional micropolygon A-buffer renderer. You can use ray intersection with them. You can actually mix PBR with micropolygon rendering as well. So there's a lot of crosstalk between the various engines as well, and you'll find that flexibility gives you a lot in terms of an artist coming to the table and trying to figure out how to leverage the best technology for your project. The other thing that we find with micropolygon renders is there's often the use of auxiliary structures to handle things like global illumination, shadows, and they're often handled through buffers or maps, shadow maps, photon maps, and point clouds. And those are often used to affect things like subsurface scattering, occlusion, and just presenting a cleaner way to represent ray trace type effects without having to dip into ray tracing as an architecture. The next engine we'll look at is ray tracing. So with ray tracing, the entire scene needs to be available for intersection testing, shading. So we have primitives that are bounded and then put into acceleration structures. And so we deal with ways of speeding up the actual process of figuring out from a given pixel what objects are intersected along the line of sight. And so acceleration structures are dealing with ways to speed up those intersection tests. So we have things like BVH, the bounding volume hierarchy. There's also options for using KD tree acceleration, which are just different ways of spatially subdividing the scene into portions that are easily manipulated and interacted with by the renderer. The other thing we find with ray tracing is because rays are directed through the scene based on light sources, they're based on BSDF evaluations, the rays are mostly incoherent in nature, and so it becomes very difficult to predict ahead of time the load and the performance characteristics of ray tracing. And so it becomes difficult to cache results, as opposed to micropolygon rendering, where you're dealing with very finely bounded problems, finely bounded primitives and fragments that you're shading. Ray tracing really does need access to the entire scene at once. The other thing with ray tracing is the shading is tied very much to your pixel sampling. For each one of your pixel samples, you are going to trace a ray into the scene, and depending on the algorithm you're using, you're going to be shading for at least once for each one of those pixel samples, as opposed to the micropolygon rendering, which can use a coarser shading metric as compared to the pixel samples. As a result, the shaders in a ray tracer are evaluated more frequently. And again, they're evaluated a bit more sporadically in terms of their scene extent. Intersection testing is happening in parallel across the entire scene, and rays are being cast all around. And so there's no real pattern or access pattern to the shading. The other thing that ray tracing introduces is the possibility of global illumination. So with scene access and with scene illumination, we can trace in reflections, refractions. We have the possibility of opening up for global illumination in terms of diffuse and specular transfer. And so all the things that you would expect out of a global illumination renderer are available with ray tracing. The other thing is choosing ray tracing as an architecture. You have support for things like implicit primitives, which can be intersected implicitly with ray intervals. You have the possibility for physical light sources and lens shaders as well, which allow you to map the way that your camera traces rays into the scene. And so non-physical lenses, we can model things like 360-degree lat-long lenses. And as you'll see a little bit later, the baking engines make use of these lens shaders to do their actual ray tracing. The next engine we'll talk about is the PBR engine. It is very much based on the ray tracing engine, makes heavy use of the trace calls in VEX. The entire PBR algorithm is written in VEX, and so it's available for manipulation as well. Custom integration engines can be integrated and extended. There are simpler metrics overall with PBR because light simulation is fixed according to physical properties. And so we're using things like the material description through the BSDF. We're using physical properties in terms of light sources, and there are fewer controls as a result to adjust in the renderer. The other thing is full light transport is possible. Because we're dealing with integration across various interfaces like materials and volumes and across geometries, there's a very generic sort of integration strategy that's happening there that can apply to a whole bunch of different media. And that allows us to do things like scatter light within volumes, which then contributes to surfaces. The entire thing is one large physical simulation. And the other big difference is the details of the light integration are handled a little bit differently compared to the ray tracing and micropolygon renderers. They are split apart from what used to be the surface shading context. In previous rendering engines, light integration was very much tied to your surface evaluation, whereas PBR really does separate surface description and materiality from your lighting simulation. And the lighting simulation is very much handled in its own sort of partition, tucked away from the user having to modify too much in terms of controls. So here's an example of how the shading is handled differently between the ray tracing engines, the rendering engines, in micropolygon ray tracing mode versus PBR. And so here we have an example surface shader. This is as you might find it as it ships with the current product. So we have the surface statement. We have the first global variable that's being assigned, which is CF, which is your global color variable. And CF in this case is just being assigned with a scalar, CD, times diffuse. Now, diffuse is a vex function. It's actually doing the light integration, and it's taking the current normal and the I vector and the roughness of the current shading model that's desired. And so the integration of lighting is happening right there on that CF assignment. So when you're dealing with micropolygon or ray tracing engines, your per pixel samples are being fed by these opacity and color values, CF and OF. Whereas when you deal with a PBR renderer, we have a global variable in vex called F. And F stands for the signature for BSDF. And a BSDF is a statistical model that determines how light scatters. And so for the PBR renderer, all that's happening is the F value is being assigned to a scalar, CD, times diffuse. And the diffuse, when it's called in vex without any arguments, is returning a diffuse BSDF. And so there's a bit of compositing that's happening there. It's a scalar times a BSDF. And there are classes for handling scales on top of BSDFs and how that affects the actual final sampling of that BSDF. So if we look at CF, the illumination is returned by the diffuse function. It's stored in the sample color. And the integration happens inside the actual surface shader. So there's no actual global context that's happening there. All the evaluation is happening in the surface. Whereas in the PBR engine, F returns the BSDF, and it's used by the path tracer, we'll look at a little bit later, during the actual light integration stage. So the PBR engine was designed around physical light transport. And so we deal with things like the solid angle, we deal with the actual energy of the light sources that are being traced through the scene. All the properties that you would expect out of a physical renderer are respected. For the most part, Monte Carlo methods are used for the simulation. Given the complexity of the integrals that we're dealing with, the only tractable method for dealing with them is really through Monte Carlo. And so Monte Carlo is essentially a statistical, a random method that allows us to approximate very complex integrals in a compact notation. And so Monte Carlo is very much based on random number generation. And we'll look at the way samplers and the way sampling within the renderer affects that. With PBR, the artist focus as well is on texturing and material descriptions. And this is a big shift in terms of paradigm. So complication that arises from some of the bias systems are things like having to tune photon map properties, photon spacing, dealing with kernels and lookups on the photon maps. You deal with noise that comes, introduce low frequency noise often from photon mapping. Historically, we've had to deal with things like shadow maps and shadow bias. Whereas when you deal with PBR, you really are dealing with a very limited set of inputs that drive the renderer. So the big difference is light integration. As we mentioned previously, where it used to be handled at the surface level, now light integration is handled globally. And that's done by a path tracer shader. Now, the path tracer shader works in a fog context in vex. And so it is present as a global shader assigned to all primitives in the scene. So the path tracer shader runs on top of everything in the scene. And that allows us to do intersection and probing of BSDF from each of the intersections. So it differs from the legacy method where the integration used to be handled locally by the surface shaders. The other thing is through PBR, there is a unidirectional path tracer that is offered as the standard implementation for our physical renderer. However, there's the option to integrate your own shaders should you desire to write your own integration scheme. And that's possible via the VM PBR shader parameter. And that's available on the Mantra ROP. And so by assigning your own shader, you can handle your own integration strategy, summing the actual input from all of the lights and calculating your own output colors and output illumination. As I mentioned, unidirectional path tracing is the integration method that's used in Mantra. And path tracing is essentially the process of following light paths through the scene as they arrive to the camera's image plane. And so there are various ways and various flavors of path tracing. Unidirectional, there's bidirectional. We have the Metropolis method as well, various ways of tracing through the scene and different ways of treating the light paths. And so with the unidirectional path tracing, it's backward tracing from the camera. And so we trace the light paths following their interactions in the scene with the materials and with the objects and with volumes and surfaces and with the media in the scene. And we want to trace the light sources back, the light paths back to the source, and sum the contributions at the actual image plane. So one of the main concepts within the path tracer is the BSDF, as we've mentioned. It is one of the essential units within the path tracing system, and it describes how light is scattered at points in the scene. So we'll spend a little bit of time looking at a BSDF and what it means. So BSDFs essentially are statistical models. And if you can look at the slide here, you can see there are different categorizations of BSDF based on their reflectance properties. We have, on the left-hand side, we have broad BSDFs that reflect light in almost uniform directions around the surface integration point. You can see the little black arrows that are there indicating the incoming direction of the light. And the blue arcs that you can see depicted are the actual response function of the BSDF. So on the left-hand side, we have even sort of BSDFs that are categorized as Lambertian, which means they're perfect diffuse reflectors, meaning that all of the incoming energy is reflected across the hemisphere, as we're dealing in this case with surface interaction. We'll talk a little bit about how that extends to volumes, but at this stage, it's dealing over 2 pi over the actual half hemisphere. So as we progress from the left, we have stronger sort of peaked functions in the BSDF. And we can see at some stage, it starts to become almost in the mirror direction. And if you look at the middle of the slide there, we can see a specular class of BSDFs. Again, this is an arbitrary division. Really, what we find in real-world materials is a very complex reflectance function. And if you look at measured BSDFs, there's been a lot of work done there, and you can actually see the polar function there is quite complex. And so what we want to do, though, is offer the building blocks and the units that can be put together to build those complex systems. And so in the middle class, we have specular reflection, which is almost entirely along the reflected direction. And on towards the right-hand side are transmissive BSDFs. And so the BSDF can also model reflection within the plane and below the plane of the surface. And so you have a very similar shape in terms of the Lambertian and specular lobes. It's just that they're happening on the backside of the surface, if you will. And so what we have, though, is if you look at the difference between the diffuse and specular, in the middle section there's a class of BSDFs that are considered glossy. And they're neither fully Lambertian or fully mirror specular. They're somewhere in between. And glossy reflections and transmission as well is quite expensive to evaluate because we're dealing with quite a broad BSDF, and we'll look at strategies for sampling that. So the BSDF, as I mentioned, models light interaction at surfaces as well as volumes. It describes how incoming light scatters at an event. It is a probability function, and so you saw those curves there. Those determine the amount of light, the magnitude of light that is scattered across the polar sphere, or the hemisphere that we're dealing with. And so what we can say is, given an input impulse of light, what is the probability that it scatters in a given direction? And so that is really the answer that the BSDF provides the renderer. The extension to volumes as well, we talked about. So rather than dealing with a local plane of interaction, volumes scatter uniformly in all directions across the entire sphere. And in those cases, instead of a BSDF, what we're talking about is a phase function. So a phase function is a probability again, but across the sphere instead of the hemisphere. And so the BSDF is sampled by the renderer to trace light paths through the scene. There are various BSDF models that are implemented in the literature and also available through Mantra. We have a class of models that tend to give us the best range of results. And so there's a good range of output reflectance models that we have that you can mix and match, and we'll look at the way compositing works with BSDFs as well. So we have things like the diffuse BSDF. We have a specular BSDF that has different microfacet models, Phong, Blin, Cone, and GGX models, each of them with their relative strengths in terms of parameters and parameterization of the reflectance. In terms of VEX, the BSDF is first-class citizen, is represented by the F global variable. So just like you would have CF and OF in terms of color and opacity, P for point, N for normal, F is a first-class BSDF variable that is assigned within a shader. So as we mentioned, real-world materials are often compound. They involve multiple lobes. They involve very complex, sometimes shapes. Things like hair shading has a very significant shape to it, an interesting shape that's quite complex. So we offer the ability within VEX to composite BSDFs together to yield the final reflectance function. So there's a quick little code example there. If you look at the bottom of the slide, BSDF F0 equals diffuse. And again, we saw that through the shader example previously where diffuse returns a Lambertian BSDF. We have a second BSDF being created, F1, equals specular with the incident I ray for the impulse. And so we take those two variables, two BSDFs, and mix and match them. So F is the output. F equals F0 times 0.5 plus F1. So the diffuse BSDF is being weighted by 0.5, then being added to the specular BSDF. And in the top right of the slide, you can see an example in the VEX network editor of one such implementation of the exact same thing you're seeing in code there. So you have the PBR diffuse node, PBR specular node, and we're just using a straight add node, which works with the BSDF data type. So you can see the data type there flagged as a yellow output, and you can see it as yellow inputs on the add. And we'll trace the way this actually runs through the evaluation. But after the add, you can see there's a compute lighting node, which is responsible for taking the BSDF and integrating the lighting locally. And so we'll look at a little bit in terms of the path tracer and the way that compute lighting works with it. And then we have the surface output, which just accepts the final BSDF value. Okay, so we're going to use an example of the BSDF compositing. So I'll just pop over to Houdini 15, and we'll take a look at what it takes to actually composite BSDFs together. So we'll just open up the first scene here. Okay, so it's a fairly simple scene. We just have a Mitsuba sphere, which is just a quick little widget that helps us to check out material assignments, and it gives us some good surfacing to evaluate shaders. If we switch over to the shop tab, we've just created a material shader authoring node here, and I'll just zoom this up here so it's easier to read. So you can see, as we discussed, what we've done with the shader is to layer the BSDF models together. So we start up at the top with PBR diffuse, which again is a Lambertian model. There are components that are associated with each of these, which match to the image plane components that are in the renderer. There's a roughness value. We've given it a bit of a reflectance color. Next we look at a PBR specular lobe. Okay, so this is using the GGX specular macrofacet model, and a fairly low roughness value, which means that it's going to be very mirror-like in terms of its shape. The next thing we've added in is another PBR specular. This is a broader specular lobe, and so the roughness is 0.5, and we've given it a bit of a reflectance value, which gives it a sort of greenish hue. And then the last thing we've done here is to model transmission. So as we looked at in terms of the BSDF spectrum, on the right-hand side, we had transmissive BSDFs. So what we've done in this case is we've taken the surface normal at the intersection, and we've negated it, we've flipped it, and we fed that into a specular lobe. So what's interesting about this is by reversing the hemisphere, we're actually tracing in the opposite direction. So the PBR specular, instead of reflecting at the surface, is now going to be reflecting below the surface. Okay, so it'll behave very much in terms of the way the GGX model does for specular. It'll have the same shape. It's just that it'll be happening below the surface. Then, as I mentioned, we have an add, which basically just takes in all the BSDF inputs and sums them together. Then we feed that into our compute lighting, and then we feed that finally into our surface output of our shader. So if we return to the render tab, we'll start a render, and we'll take a look at what the result looks like. Okay, so we've just stopped the render portion partway through just to give you an idea of what the final output looks like. So as you can see, the actual final shaded result and the materiality is fairly complex. We have a lot of different features. We have some soft reflections here, some blurry, glossy reflections with that sort of green lobe that we looked at. We have fairly sharp reflections around the terminator, around the edge of the surface here. We have an underlying sort of diffuse shading that we can see here. And then down below, you can see a little bit of hint of the transmission that's happening through the material. And so what you can see is with the compositing of this BSDF, it gives you the ability to create some fairly complex materials and reflectance functions. Again, this isn't probably the most representative of a real material, but it gives you an idea and a feel for how these materials can be combined. So I think what we'll probably do right now is I'll just show you what each of these looks like in isolation, just so you can appreciate how they're all combined. So we'll just render that again. So the first one we'll look at is just the PBR diffuse being shaded on its own. So you can see it's Lambertian in terms of its reflectance properties. We have diffuse bounce happening through here, through the bottom of the shape, a very flat, sort of even tone throughout. The second specular, or the first specular lobe, rather, the second BSDF, is the one that was giving us the glossy sort of coat kind of look to the edge of it. You can see it gives it that sort of wet metal sort of paint look. Now the second specular is the one that had the broad sort of shape, sort of like a metallic green. And you can see that's where our soft glossy shadows were coming from here. Glossy reflections, rather. And the final lobe, which was the transmissive lobe, was giving us our refractions that were coming through the transmission. So you can see some of the surface plane here, the checkered plane, being picked up through the object, almost like a partly translucent plastic. And so on the whole, mixing these all together gives you that complex behavior that we're interested in. So now we've looked at a little bit of the BSDF and the way that we can composite BSDFs together to build up materiality and build up reflectance models that give us a lot of flexibility in terms of the look of our shading. We'll spend a bit of time talking about the unidirectional path tracing method. So again, it's a backward tracing method that's progressing from the primary camera rays back through the scene, tracing light path interactions. And so for each primary ray on the image plane, we generate rays from the subsamples on the image plane and trace into the scene. And so the algorithm works this way. While the ray is intersecting the scene and hasn't exited the scene, we trace the path. So starting with the actual eye ray, we trace into the scene, we find our intersection, and we sample the F variable at that intersection, which is the BSDF. Okay, and so at each of the intersections with the geometry in the scene, we pick up the BSDF, and we have properties in VEX that allow us to sample the outgoing illumination direction. We have the PDF and the reflectance values that we can look at that give us a hint in terms of the way to import and sample the BSDF and the way to distribute rays that gives us the best final sum. And so once we've sampled the BSDF at the intersection, we sum the emission and the direct illumination that's happening at that surface interaction. And we weight that by the BSDF to give us the final weighting of the illumination at that point. Then from the BSDF, we generate a new path direction. And this is where we feed the Monte Carlo portion of it in to the model. And so we have random samplers that feed in values that generate new path directions based on the BSDF. And so when we're dealing with diffuse BSDFs, those paths are going to be quite broad in terms of the way they spread into the scene, progressing more towards specular BSDFs, which are mirror directions in terms of the samples they generate. So there's a few observations we can make about the path tracing method. It's iterative. So what we find with path tracing is successive results are all valid, meaning that regardless of the number of rays that we send into the scene, each one of those packets or each one of those illumination samples that's being taken is valid on its own. When taken on the whole, what happens is the solution converges with enough of those samples. And so even though we're feeding it random values, those random values, when accumulated together, give us a best estimate of the integral of the actual lighting function through the scene. And so often we have to trace quite a few samples in to reduce the noise, to produce a high enough fidelity result. But the idea is that through each iteration, we can add to the accuracy of the simulation. The other thing we notice about path tracing is it's deeply recursive. And so you can see starting from the initial root path at the eye We have paths that can progress quite deep into the scene in terms of the number of bounces. So we have to look at things like termination strategies to limit the recursion depth, things like Russian roulette, other methods for dealing with once the actual contribution is low enough, looking at ways to taper off and drop out certain path samples. The other thing is PBR unidirectional path traced images are characterized by the level of variance or noise in them. That comes about as a result of the use of noise to generate those random paths. And so often what we're doing is finding strategies for reducing the amount of noise in the image. And we'll look at strategies for that in a little bit. The other thing about unidirectional path tracing is because we're starting from the camera, it's difficult to resolve paths or light paths that begin at the light sources. And so if you have a light source that's concealed or embedded, occluded by something, it's unlikely that on sort of the random sampling that we'll end up back at that light source. And so focus caustics depend quite a bit on light centric paths. So focus caustics, very high, sort of sharp caustic highlights are not well represented within the unidirectional path tracing method. However, broad specular transfer is possible. It's just that other strategies become probably more suited towards dealing with paths that begin at the light sources as well as the camera. And we look at things like bidirectional path tracing in that sense. Okay, so we're going to spend a bit of time looking at light paths in a scene. So we have an example scene here, and I'll just pop over to Houdini 15, and we'll take a look at what happens when we trace through a realistic scene with a variety of material descriptions and BSDFs that we were discussing earlier. So again, we have the Matsubara sphere. We have three shader balls that we're dealing with, a diffuse on the left, a reflective, glossy reflective in the middle, and a refractive sphere on the right. And we'll just do a quick render of that and show you what each of those is looking like. Before I do that, I'm just going to have to turn off some of these objects here that we'll look at in a little bit. These are going to give you an idea of what light paths look like within the renderer. And hopefully it'll give you some insight into the way that the sampling happens. Okay, so we can see on the left, again, this is very much a diffuse Lambertian surface, glossy reflective, and a transmissive surface, which is dealing mainly with refractions. So you can see the object in behind it, the checkers being refracted. Okay, so what we've done is we've modified the path tracer to output intermediate paths. And so we've baked out, as the renderer was running, point clouds. And the point clouds give us the ability to visualize what the rays look like. So let me just turn on visualization here. Create a marker. So we've created a visualizer for the point cloud. And what we're looking at here in the first example is the diffuse paths that are being integrated. So let's just close that. We'll turn it on only for selected objects, the visualizer. So let's have a quick look. The first point cloud here is the rays that are being traced out from the diffuse surface. And so what we've done is we've taken a pixel in the image, which is sort of towards the bottom. You can see where all the rays are converging. And we've output the paths that are from the renderer. Maybe that gives you a better view of it there. And so you can see the way the light paths are bouncing around the scene. In the diffuse case, they're quite broad. The paths are not confined to a certain angle. They traverse the scene in a variety of directions. What we have here is the actual breadth first look at the way samples are cast out from that point. So what we've done here is sample the BSDF recursively for a single point, which is the first intersection point. And what you can see is everything's spreading out in a sort of uniform hemisphere around the point. We have a bit of a fall-off function where you can hopefully see that it's denser at the center. It's cosine weighted according to the lobe. And things taper off towards the edge of the hemisphere. So what you can think of is this is the way the path tracer is sampling each of the BSDFs. So if we sampled the BSDF, and this is 512 samples all at once, this is the distribution we would get. So that's the overall shape of reflection that we can expect. And again, looking at the next point cloud, this is the direction that the light paths, each of them has taken. from those original source rays. So that's for the diffuse example. We'll look next at the reflection. So the reflective surface, we picked a pixel sample that was right at the edge of the object because we wanted to look at the mirror reflection direction and the way the rays are cast in that case. So hopefully you can see here that on the edge of the surface, the rays are being cast sideways off towards this object here. So again, you can see a bit of a fall-off function. Most of the rays are towards the specular mirror direction. We have a few, because it is a glossy lobe, we have a few stray paths towards the outside here, giving us the feathering or the soft kind of look to it. And if we look at those paths themselves, where they actually end up, there's no mystery here. We have them emitting from this point and reflecting off this object here. So you can see there are a few cases where after they've reflected on this object, they then intersect with the back wall. Just back up a little bit there. There you can see. So these are deep rays in terms of ray depth. This would be ray depth 1 here, 2, 3, and then it progresses based on the limits you've set in your scene. Okay, so hopefully what this is giving you is an idea of the way the BSDF influences the light transport in the scene. The last object we'll look at is the refractive object. Let's just turn into wireframe mode here just so we can get a better view. So in this case, what we have is rays being cast into the object. So hopefully you can see in the yellow there, the rays interacting at the outside surface here, being cast inward. And again, we used PBR specular as the model for transmission. So a very similar shape to what we had in the reflective object as well. And if we look at the paths that these light rays took, we can see they interact at each of the surfaces. You have them bouncing here, interacting here, and refracting, and progressing outwards and intersecting with the back wall. Okay, so that gives you an idea of the way a transmissive object influences the light paths. So if we look at it in the whole, we can understand that when we're doing path tracing, it really is the sampling of the BSDFs and following those light paths back through the scene to work out how light is transmitted, how radiance is accumulated through the camera. Okay, so returning to the slides, we'll just do a quick overview. So you can see here in red marked the pixels that were sampled. We have the various lobes, the diffuse lobe. These are the diffuse points that were sampled. The reflective lobe, the reflected points within the scene that were traced, and the transmissive lobe and the transmissive points that were sampled. So one of the things that we deal with in terms of PBR renders is the amount of noise that comes as a result of the Monte Carlo basis. So as we mentioned before, oftentimes scenes have a large degree of complexity in terms of the lighting and geometric details that lead to a fair amount of noise that can be present in the renders. So that's termed variance. And in general, it's a measure of how well converged the solution is. So the idea is that the more variance you have in a given integral, the less certain you are about the actual estimate of the underlying function that's being estimated. So when we look at the rendering, we find that variance comes in through a variety of sources. We can have things like geometric boundaries introducing variance. We have light boundaries, things like shadows. We can have features within our HDRI lights that are peaked, say hotspots that might introduce some variance. We also have things like shading features like high contrast textures that can be problematic because essentially each one of those random paths can be intersecting a different part of the scene. And if that part of the scene introduces a high degree of variance or high degree of illumination back through the path, then when it's averaged together, it ends up biasing it towards that peaked function. And so we have things like broad BSDF lobes because when we looked at the Lambert function, we can see that we're sampling over a great degree of the hemisphere. And so there's more chance of each one of those paths intersecting high variance or high illumination segments of the scene. We also have stray specular paths, which introduce artifacts like fireflies that we see. And that's just specular reflections carrying on through the scene and summing quite high illumination values. So variance has a counterpart vex function titled variance, which computes values at adjacent pixel samples. And so as we're doing our path tracing, because we're dealing with a global shader, in that sense, a fog context, the root path looks at the current estimate of the illumination coming through that pixel, and it can look at the adjacent values in adjacent pixel samples. So what we can do is we can look at that neighborhood within the pixel space and say, what sort of variance are we seeing? Are there spikes in terms of illumination? Do we need to do more sampling there to reduce that variance? And so we use it as a local quality metric, and it informs the sampling of our paths. So we say, for example, in pseudocode, while the variance is above a threshold, we sample more paths, we average more results. And hopefully, as a result of tracing more paths through the scene, we average out any spikes in terms of illumination. So the mantra parameters that you're interested in are called noise level. VM variance is the parameter name, the actual parameter itself. And so lower noise levels reduce the amount of variance or tolerance that is allowed for any given pixel. So those are the ones you want to tune. The other thing that we'll look at in Houdini 15 is something that we spent a bit of time on, introducing quality metrics. This is built on top of the whole idea of variance in terms of tracking the variance. However, the initial implementation was tracking variance globally per pixel without respect to what the source of that variance was. Whereas in Houdini 15, what we're doing is we're offering metrics that say, let's measure the variance, but let's measure it per component. Okay, so we have the diffuse, reflection, and refraction components, which are just saying, classifying broadly the way the paths are being treated in the renderer. Diffuse paths coming from Lambertian type, BSDFs, reflection coming from specular and reflective lobes, and refraction coming from transmissive lobes. And so what we can do is look at each of those and figure out where the variance is coming from. Is it coming from the diffuse? Is it coming from the refraction? And it allows us to get a better estimate of the source and the degree of the variance. Okay, and so that allows the sampling to be directed at the noisy components. Okay, so from an artist's perspective, you know, looking at the image, if the noise is coming from, say, reflections, and that allows you to adjust quality settings per component. So quality, the way it works is it modifies both the noise threshold that we looked at before, the noise level, and it modifies the min and max samples that are being used by the renderer. So when we're doing variance ray tracing and anti-aliasing, we have a min and max amount of rays to spend. And what that says is that we'll always trace the minimum amount of samples, but if we find samples with a lot of variance in them, we will trace additional rays up to the max. Okay, so with quality, what we're saying is the noise level is 1 over the quality, which makes sense. So we're reducing the noise level based on the quality. So twice the amount of quality is half the noise. And then we're also multiplying the min and max samples by the quality. So twice the quality would double the amount of min and max samples. Okay, so quality acts as a sort of global override over some of the other parameters that are influencing your quality in the PBR renders. So the mantra parameters that are relevant are diffuse quality, reflection quality, refraction quality. Okay, and so these are available as per object as well as at the global scope on the ROP. So that gives you the flexibility to isolate individual objects that are causing problems. So you can say, isolate that object, attach that parameter to it, the rendering parameter, and tune it and get the right result, get a smoother result out of the render. Okay, so just going on the topic of quality metrics, we're going to return to Houdini and we're going to open a scene file that shows how the quality metrics are handled. Okay, so we've opened up our scene file here. Again, it's using the same sphere setup that we're using for the BSDF and the path tracing examples. So let's take a quick look at our scene. We'll just render that. We'll switch over to the output tab. Just look at our mantra settings. Okay, so again, we've selected physically based rendering for this case. And our settings here are diffuse quality, reflection quality, and refraction quality. So let's just do a baseline render just to get an idea of what that looks like. So what we've done in this case is we've set the pixel samples to 1 and 1. And the reasoning behind this is what we want to see is the actual raw sampling performance as opposed to upping our pixel samples, which always gives us a smoother result. What we're interested in seeing here is the quality settings as they influence each of these types of paths that are being traced. So again, diffuse, reflection, and refraction. So let's just store this snapshot. And we're going to increase the diffuse quality. We'll go up by a factor of 3 in this case. So you're going to see it update now. And hopefully what we're noticing is on the diffuse ball here on the left-hand side, we should end up with quite a bit less noise in the final render. Okay, so what we'll do is we'll zoom into this area and we'll just rock back and forth between the two images just to see the difference and the improvement. So you can see in this case, the variance has been reduced in this area. It's quite a bit smoother in terms of the results. And so that's, again, just treating those diffuse rays differently from the other rays in terms of the quality settings. So we'll do the same for reflection now. Let's just up reflection to 3 as well. And we'll drop diffuse quality back to 1. And we'll just look at reflection on its own and just see how that's influenced by the quality settings. So here we're comparing the original render and the updated render with a quality of 3 for reflections. So you can see reflective quality is quite a bit better. And we'll now do the same thing for refractions. So we'll set a refraction quality to 3 and see how that influences the shading. And so we can see here, compared with the original render, we can see a reduction in terms of the amount of variance, much better quality shading. And as we can see, this is influencing just the refractive component of our shading. So that gives us an idea of the quality settings and the way that they can be used to influence quality per component. That gives you the flexibility to be able to tune your scene, address the noise as you see it as the artist, without having the renderer try to make second guesses about where the variance is coming from in your scene. So it gives you a great degree of flexibility in terms of controlling quality. The next thing we'll look at is adaptive sampling. So this is a method that's aimed at towards reducing variance in the scene again. In this case, instead of looking at the components themselves, we're looking at the path features. As the path is being traced through the scene, we can make certain estimates in terms of the amount of variance being introduced, what points of the scene it's being introduced at. And so that gives us some clues in terms of guiding the sampling and trying to minimize that amount of variance. This is accomplished by path sampling in 2 passes. Okay, so the first pass is the traditional unidirectional path tracing evaluation. So we sample the BSDF and we progress through the path trace as normal. We sample the BSDF randomly through the Monte Carlo method, and we store the resulting luminance locally in a grid. And that grid is stored at the root path. It's done locally and it's once per path. Okay, so we store an 8x8 grid that represents the spatial variation throughout the path. The second pass then uses that grid to direct the sampling in the areas where the illumination is varying quickly and where we have a high degree of variance being introduced. Okay, and so the overall effect is to smooth the sampling quality, and it reduces the amount of noise in the images, and it also, as a result, means that you converge more quicker to the results. So there's an even number of samples devoted to each path, so we basically split the min and max samples in half. We say half go towards the initial probe sampling, and half go towards the second guided sampling. There are 2 new mantra parameters that control this behavior. There's an adaptive sampling flag, which you can see here is just a toggle, and there's an adaptive sampling threshold. And the threshold basically says within that grid, where are the interesting features? And so we say measured across the actual sampling domain, when we find features that are greater than a certain luminance, we trigger the adaptive sampling method. And so that value there, the threshold, determines how much of a change before we actually try to resample. So I'm going to try to show you some examples here that detail the differences between the standard and adaptive sampling. So the first example here is the Sponza atrium that's been rendered with standard, and here with adaptive method. The adaptive method, you can see, produces quite a bit less noise, and hopefully we'll zoom in and see some tiles that show close-ups of the way the sampling is influenced, and we'll see the effect that has on the final samples. Let's switch over to a tile here. So we have 4 tiles that were just chosen out of the original images. The first one here is the standard sampling, Monte Carlo path tracing. And the second image here, as I'm showing you, is the adaptive sampling. So as you can see, there are features of the first set of tiles that show off some clumping in some of the sampling areas. We can see some dark splotches, unevenness in terms of the samples that are being generated. In the adaptive sampling, a lot of those features have been evened out, and we can see an overall sort of reduction in terms of the overall noise that's present in the image. So I'll just go back and forth a couple times here, give you an idea of the effect that the feature has. Great. Okay, so the next topic is texture baking, which is a big extension in Mantra 15 and Houdini 15. Essentially, texture baking is concerned with rendering not through cameras, but through the actual surface plane. And so what we're doing is we're baking out surface features, texturing, shading into UV maps that can be reapplied to models that basically would take complex shading and reduce it to a texture map. And so this can be useful for a variety of applications, illumination baking, geometric features. We can bake out normals. We can bake out high resolution mesh detail, and then apply that to low resolution meshes, which helps with level of detail models that we might want to build. And so we can also do things like flatten procedural texturing and procedural workflows into texture maps. And so it's a level of detail technique that tends to be used quite a bit in games and VFX as well. So the question is, how do we render a UV image or a texture-baked image? So the overall concept is we move a camera over each pixel, we send a ray into the UV image, we compute the color, and we store the color in the pixel. So it's a little bit different from traditional main camera rendering. We use a Mantra lens shader. So again, the texture baking relies heavily on ray tracing features. And what the lens shader allows you to do is displace or modify image plane samples. And so instead of rendering across a grid or the near clipping plane, you can imagine, what we're doing is we're taking each of those UV samples on the image plane and producing a new ray direction for it. And so we can do things like non-physical lenses. We can do fisheye lenses. We can do all sorts of interesting things with them. So the UV rendering, or the texture baking, relies on this to place image samples above an object. And so you can look here on the left-hand side, CVEX function, which is responsible for doing the UV lens placement. So we take in the current UV sample in the image plane and we unwrap it. So the relevant interesting function there is the VEX UV unwrap function, which takes a U and V value and some other state variables and computes a new direction. And so for each one of these UV samples, we end up producing a ray that traces down onto the object. So the algorithm looks like this for each pixel. And for each sample in each pixel, we compute a camera ray. And this is the traditional rendering algorithm. We send a ray into the scene. We store the final color into a sample. We sample those pixel samples, image samples, into the final pixel value, and we store that pixel in the image. So UV rendering is a little bit different. We'll look at that in a little bit. But first of all, there's a few different options in terms of the way to output texture baking or baked values. We have support for Ptex, which allows us to bake out face relative color values. We can also bake to mesh colors or point colors. So if we want per vertex coloring, let's say. And then we also have support for UDIM or UV tile maps, which have a UV atlas, essentially, which allows you to split the object into many different UV tiles. And so as we compare, as we looked previously, this is a UV rendering algorithm. So now instead of rendering for the image, we're rendering for each texture image. And we'll look at the way the ROP is set up, which basically allows you to specify a whole group of objects that you want to process. But for each of those texture images, for each pixel, for each sample in each pixel, we compute the camera ray. We call UV unwrap, and this is where the lens shader comes into play. We send the ray into the scene. We store the color in a sample. We filter those samples into a pixel. We store the pixel in the image, and we set up UV unwrap for the next image. So the UV unwrap has to have some smarts about the geometry that's being processed that allows the algorithm to unwrap the rays. So UV render uses Mantra. This is important to understand. UV rendering is Mantra rendering. There's no separate process that's started. We're essentially just changing the way that the lens traces rays into the scene. And so because it is a Mantra render, all the normal features and algorithms are available. We have deep raster planes. We have PBR ray tracing available. We have sampling quality, motion blur. Everything that you've come to expect of the Mantra renderer is available through the UV rendering workflow. There are some subtle differences with UV rendering. We automatically mark all objects except the UV image as phantom. and that's to prevent any self-intersections with other objects. That doesn't mean that you can't reflect other objects in the UV baked image, but the UV image itself is the primary object that's visible. The other thing that's a bit different is the refinement measuring. Because we're dealing with a non-physical lens, the ray derivatives have to be used to estimate the way the refinement happens to the mesh. The other thing is displacement and subdivision surface rendering. We have introduced the concept of UV bias. Now, what that says is that the geometric normal and the geometric position of our lens may actually end up buried within the surface after displacement has been evaluated. And so we allow a bias to be introduced where we push along the normal of the surface to get ourselves out of intersection with things like displacement or subdivision refinement. And so there's also an option to reverse normals if you want, so you're tracing the opposite direction. This is useful in the cases where you somehow have reverse normal primitive data. And then we also hide the UV rendering ROP from the viewport menu. So it's not one of the common outputs that you want to have appearing in your IPR renders. There is support for multiple UV objects, and there's pattern expansion available. So we'll show you in the ROP in a little bit, but there's essentially, you choose the UV object that you're using as the source to trace from, and that accepts wildcards expansion. So you can say obj geo / and then star, let's say, it'll pick up all of your geometry objects. And then there's an output image that's specified, and that can also use wildcard expansion, which is great for scene processing. The UDIM or MIP mapping, essentially what happens is as we're baking down these textures, we're essentially shading geometry that matches the UV islands or the UV shells as you see them on the right-hand side. What happens is pixel filtering then blends against a black background. So what we end up with is a fringe of anti-aliasing that essentially is blended to black in terms of color. So when MIP mapping then takes over, what you have is area estimates that are filtering against black, essentially. So you can see on the left-hand side, this introduces texture seams. And so we have a black line sort of outlining all the UV islands or UV borders. We have an option in the ROP to support expansion or padding. So this is basically a pixel padding that's added around each of the islands that smears the edge pixel values and gives you a bit of a buffer. And that buffer is important because it allows you to blend across those map tiles correctly. The other output method we have is for Ptex. And Ptex output is essentially a raster image per face. And it's face-oriented. And we support things like varying resolution based on face area. The way we work out resolution is we measure each polygon's area in the mesh. The smallest polygon gets the minimum resolution you've specified. And then everything else is linearly related to that. So if a polygon is twice as big as that, its resolution will be twice as large. Okay, so with a scale of 2, if a polygon is twice as large, the resolution will be 4 times larger. With a scale of 0, all polygons will be the same resolution. So we don't do any adaptive face scaling in that sense. Everything that gets output is the same size tile. And then face orientation is important as well. So the way the Ptex rendering works is we render a large image with lots of individual tiles. Each tile represents the face texture values as they vary across the face. And then those are post-processed to generate the final Ptex file, which is a gigantic atlas that you're seeing displayed on the left-hand side there. And each of those indexes a different face. The other thing that's tremendously useful with texture baking is to deal with a hierarchy of meshes. And so often what we want to do is take a low-res cage object versus high-res geometry, and we want to bake between the two of them. We want to say take the high-res features and bake them into the UVs of the low-res map. Okay, and so the low-res geometry receives higher frequency detail, and we can do things like supply that to games engines, supply that to a level of detail models, where we substitute our detail for textures. So here's the support for that within Mantra. We have low-res cage UVs, which in this case you can see on the UV view there in MPlay. There are 6 tiles there. They're quite broad, quite simple UVs. And what we're going to be tracing against is, you can see on the left-hand side there, a very highly subdivided and displaced sphere, which is a sub-D version of the cage. So we have the constant shaded cage, which is going to serve as the UV source for us. And we have the sub-D in the viewport. So that's the representation of the subdivided mesh. And to that, we'll be adding displacement and lighting. Okay, so after baking out, we're able to take the flattened illumination map and instance that through the scene. So we can create copies of that geometry and place it throughout the scene and have it look like the lighting is actually baked into those objects. The other thing that becomes important when we're dealing with UV baking and UV texturing is surface baking. And so the goal of surface baking is to take high detailed features and represent them as texture maps. And so we have a lot of geometric workflows where we're dealing with super high resolution meshes. We have packages that deal with sculpting in millions of polygons, and we're dealing with very fine features. What we'd like to do is be able to encode all of those features as texture maps and apply them to a low-res cage object or decimated or retopologized mesh. Okay, so we're baking, in this case, shading, but we're also baking geometric features, not just the illumination. So things like normals, we want to look at the occlusion, we want to look at curvature. These are all things that we want to bake into our geometric maps. Okay, so this technique has been used extensively in games production, and it's used to allow extraction of high-res meshes to low-res geometry or low-res assets. Surface baking like this is offered in a range of modeling packages that you've probably had experience with. We find it in ZBrush and the ZBaker. We have Mudbox, 3D Coat, XNormal. They all offer some form of this geometry extraction or surface baking. And so surface baking opens up some new opportunities for us in terms of Houdini. It's a good fit. We can generate high-res procedural details, high-res procedural models, and bake those down into texture maps that are ready for games engines. So one of the important things we deal with in terms of baking down to texture is the texture space that we deal with. We have the UV space, which our maps are ending up in. One of the complement sort of techniques that are being used is a tangent space. And so tangent space is essentially the tangent plane that lies in the plane of the surface. Okay, so the technique is about storing normals or other data in the tangent plane of the surface instead of in world space or in object space. The tangent plane, as we look at it, you can see it on the right-hand side depicted there. That is a tangent plane in terms of the normal. Now, the tangent plane can rotate about the normal, and so it's undefined in terms of its orientation. So what we do is we take the UVs and the UV derivatives, and those provide the consistent basis. Okay, so our tangent plane always flows along the UV direction. The expression of normals in tangent space has advantages. Okay, so you can encode costly operations like bump mapping as a texture map. So all you're doing is substituting based on the local tangent plane, you're applying the new normal that needs to be applied. Okay, so the alternative would be to use fragment shaders or to do your bump mapping, which is quite expensive. And so this offers the advantage of encoding that as a texture. We have deformation of geometry without need to recalculate our normals. Because we can calculate in our model export the tangent vectors, those tangent vectors are always relative to the vertices, and so we don't need to recalculate our normals as our vertices or vertex shaders are deforming the meshes. We can also encode high-res surface features as textures, as we discussed. Okay, so these are the advantages of using tangent space normals. This is supported in Houdini 15 in a variety of places. We have VOPs that allow you to project into the tangent plane and project out of the tangent plane. We have the texture baking that we're looking at now. We also have support for tangent space normals in the mantra surface and principled shaders. And we also have support in our OpenGL viewport rendering for tangent space normal maps. And we'll look at that in a little bit. So to help facilitate baking in Houdini and baking, especially of as we talked about surface details, we have a bake shader, which represents common baking tasks. And the shader deals with evaluating the projection between the high-res surface and the low-res surface. So the cage and then the high-res detail surface you're working with. We're looking towards multiple surface correspondence methods. And so what we need to do is establish for each point in the low-res mesh, where on the high-res mesh do we end up when we're shading. So one of our initial methods is to use ray tracing along the surface normal. Okay, so we trace rays forward and backward along the surface to find where on the high-res surface we should be shading. Downside with this is it doesn't deal well with local curvature and high curvature areas. So in this case, we need to look at other correspondence methods, one being UV projection, where we say UV shells exist between the high-res and the low-res, so we can easily associate one point with the other. And then the other method is to use a closest point approach to establish correspondence. So With these other two methods, you can do things like vector displacement and dealing with overhangs and high curvature areas. The bake shader offers a set of common output types. We have displacement, which calculates the difference between the two high-res and low-res mesh. We encode normals. We can encode the tangent normals, as we discussed. We have options for occlusion, cavity shading, and thickness. And so in terms of authoring PBR textures, this is important because often these feed as inputs to shading pipelines within the engine. So the bake shader gives us a good sort of first look at some of the common baking operations that you want to do. So here's an example of an output from bake shader. This is a very high-res character mesh, which was roughly 6 million polygons, baked down onto a 6,000 polygon decimated version. And so you're seeing lots of folds and creases and feature details that are introduced. Here's a quick overview of some of the output types that the shader has. We have displacement, we have normals, which can be encoded in either world space or local object space. We have tangent normals that are available. We have occlusion. We have cavity mapping, which gives you sort of relief mapping or high curvature sort of areas that are shaded in sort of high relief. And then we have a thickness map, which is useful for things like subsurface scattering. You can shade thinner areas in a different method. So what we're going to do is open up a scene that shows off the surface baking features. It's a fairly high-res scene. You can see here compared 6,272 polygons in terms of the decimated mesh. And the high-res mesh, which came out of ZBrush, was 6,422,528 polygons. So I'm just going to pop over to Houdini, and I'm going to show you what that looks like and how we interact with it. So I've loaded the asset here. It's quite heavy, so I apologize. We'll probably have to fast forward a little bit. I'll show you the two meshes. This is the low-res mesh. And again, it's about 6,000 polys. We've added a subdivide node, and I'll explain what that's about in just a little bit. Here's the high-res mesh, just as comparison. Just take a little while to display. Just highlight it for you here so you can see the intersection and the way the planes work with each other. The high-res mesh having quite a bit more detail and wrinkles and things that you want to sort of bake down. So what we do is I'll show you how to set up the texture ROP, bake texture ROP. So we go to our output tab and put down a bake texture node. Okay, so the bake texture node has a few parameters here that we're interested in. This resolution here controls the resolution of the output baked images. So we'll just leave that as default for now. When we talked about the bake shader, we have it integrated into the bake ROP. Just add the flexibility there if you want to output certain common bake types like normals. What we'll do is we'll set up a few of these inputs here. The samples here control the number of ray trace samples that are being used for things like occlusion. The normal space we want to keep 0 to 1, let's say. We'll set the occlusion bias, which just biases the actual final occlusion value to say, make it a bit darker than it normally would appear. Cavity distance gives us a normalized range across which to shade the relief features. Again, bias is sort of like a threshold or a power function. And a thickness max, which gives us, again, a normalized range output. So that's the control for the surface. The way the baking is set up is through a multi-parm here through each of the UV objects that you want to bake. So in this case, what we're going to do is choose our UV object to be our low res and our high res object to be our high res. Okay, so this is going to use the UVs of this object traced down against the high res object. And then our output image, let's just try outputting to an EXR. And the way the bake shader works is under the Images Extra Image Planes tab, we've added some baking specific channels that you can output. Displacement, shading unit normal, which is just surface normals, the tangent space normal. There's an occlusion option, cavity option, and thickness. And by toggling each of these, you're just triggering the outputs of the bake shader to output that channel. So our final image will contain the baked image of the UV rendering and a set of image planes, which represent all of the bake output features. So once you've set that all up, you just click Render to Disk to launch a baking process. Okay, so I've opened up the resulting bake image here. The bake shader by default in the C plane just outputs a black image, but as you can see here, the image planes that we specified have been baked out. So we'll just go through them so you can see some of the options. So the NT plane is the tangent space normals. So again, you can see the extracted detail in terms of wrinkles and folds that have been output. Lots of detail that'll be baked down onto the low-res image, high-resolution detail. The NU image is the normals, and these are normalized again, 0 to 1. Depending on your engine, you may need to bake those in -1 to 1 space. DS is displacement. Displacement calculates the difference along the normal between the low-res cage and the high-res object. So you can see things like little blemishes here and there appearing as little bulbous kind of features, and dark features receding away from the surface plane for wrinkles. This can be applied as a traditional displacement map in a renderer. OC, which is occlusion. There are controls there for the amount of bias to give you darker sort of features in the occlusion if you're interested. CV, which is the cavity render. Again, gives you a lot of surface details, wrinkles, folds, and all of that in high relief. And this can be used as an interesting way to blend between, let's say, scratch maps or dirt maps in your shading. And then the final output, which is thickness. You can see here the lids of the eyes being quite thin, portions of the head being thicker, tips of the ears quite thin. And this again can be used for things like mapping subsurface scattering. So what we'll do is we'll go back to the object view now, and we'll show you some of the features within the Mantra surface shader. So what we've done here is we've created a copy of the low-res mesh, you can see here, which is the shaded version, which incorporates the normal map that was baked out. So I'll just take the material off to begin with. So you can see here it's quite low res. Not a lot of polygons to deal with, but it is exactly the workflow that we're interested in. I'll attach the Mantra surface now, and you can actually see the displaced detail there. It's quite strong. There's lots of detail in there, lots of folds. You're getting all of the details that you saw in the high-resolution mesh visible through the low-resolution polygon mesh. Okay, so this is fantastic for level of detail, for preparing game assets, and hopefully bring some exciting features in terms of baking. So let's take a look at the Mantra surface that is assigned to it. So the Mantra surface shader has a tab here, bump in normals, and we've enabled here normals, and the texture type is a normal map. What we've done is we've specified the UV tangent space, which is the default, and we've just navigated to our baked out tangent space map, and that's all that's required. So I'll just pop back over the presentation now and just show you what that looks like rendered. So again, just comparing the output, we have our shaded mesh on the right-hand side and the high-res mesh in the middle and our cage mesh on the left. Okay, so there's the Mantra render, or rather the viewport render of the three. You can see the surface shading features being preserved quite well in the viewport renderer. And then we have the Mantra render of the same. And so whether or not you're dealing with the viewport or the Mantra offline renderer, you're going to get the same high quality results out of the tangent space normal maps. Okay, so it gives you a lot of options in terms of PBR texturing and flattening out your images with baking, but also the ability to encode geometric features and really match one-to-one a lot of the modeling features you're seeing in some of the other packages. Just coming to our last feature we're going to highlight, added to Mantra and Houdini 15, there is the option for render checkpointing, which is a huge addition. It's a great time saver in terms of dealing with image maps or image renders that have failed, that need to be restarted and resumed from a checkpointed position. So the notion behind it is that we store partial results and pixel samples from interrupted renders. The temporary tiles that are currently active in the renderer are flushed to disk at specified intervals. And so we have basically an image file that lives alongside the image that's being rendered that contains all this state information. And so when we come to restart the render, we have the option to resume the render from partial results. Okay, so let's say you've rendered quite a complex scene. You get to the 90% mark, and let's say you've run out of memory. you're missing textures, you realize there's something that is amiss in the render, what you can do is restart the render from the 90% mark, adjust your system environment, adjust settings that you're interested in, and then resume the render from that point. Obviously, you don't want to be changing too much that would affect the visual look of the final image, but things like memory that you can address are all sort of valid edits that you'd be making. The render checkpointing is supported for native image formats within Houdini, which includes PIC and RAT textures, as well as for the OpenEXR image type. So what you'll notice is in your renders now by default, and if you'll find this in the rendering tab under output, there is a toggle there for output checkpoint files. So by default, Mantra will always be rendering these for you, and they're stored alongside your image. So you'll have your image name .mantra checkpoint file. And those files are what is used to restore the state. You have to currently toggle on to restore from those files. There's just a toggle below the output checkpoint files called resume from checkpoint files. And by toggling that on, the renderer will then load all those tiles into memory and continue on from where it left off. This also is paralleled by a new HQ option called enable checkpoints. And when on, which is the default, HQ resumes the renders from those points when it's rescheduled. Okay, so that concludes our look at Mantra for Houdini 15. Hope you've enjoyed it. Hope you've enjoyed a look at some of the new features and the exciting possibilities that it opens up for you. In production, we have here just a slide here with future further resources for you. We have things that will help you alongside learning the renderer Mantra. We have the Mantra user guide, which is available, which is an excellent reference, has a lot of visual sort of touchstones in terms of diagrams and things that walk you through the way the rendering process works and how Mantra can be tuned. We have a page on Houdini 15 rendering, which is dedicated towards various topics in rendering. We have what's new in Houdini 15 rendering, and that will detail some of the features that we went through today. Another thing that's quite prominent is shading. We did discuss the way that shading works with PBR. So there's a whole page on the way shaders work and how to author them. And then, of course, there's the Houdini forum where we have lively discussion about everything that's gone on with the renderer and everything that's Houdini. And so we encourage you to get involved and let us know how things are going and how you like the renderer. And that concludes our presentation. Hope you've enjoyed it. Thanks.